Hi, everybody. Welcome. This is Tuesday morning, the 23rd of June. A couple of quick announcements. There's the 7th, this is the second to last homework, believe it or not, which is due on tomorrow evening. And then there's another exam on Thursday morning, which will cover material through the homework from last weekend. So basically systems and the basics of rotational motion, but not the details of how you solve problems technically using the second law, which we're doing now and which we will continue to do for the next day or two. Let's see. I've got a couple of problems I'd like to work through today and just have people follow along. Again, I'll post these as practice problems. I already wrote up the two from yesterday. I just haven't had a chance to post them. I was going to try to get that done this morning, but my internet was a little flaky. So we'll try again right after class. But I'll write these ones up as well. The first problem is a problem which I'll call rod on a hinge. Okay. So what does this problem look like? So what I do is I'll set up a situation where I've got a wall or a ledge, if you will. And then I'm going to invent or describe an object, which I will draw in, I guess I'll keep drawing this in white, which is basically a bracket with an axle on it. And we'll call this a hinge. Okay, so this is basically just some hard point that will hold one end of a thin rod. There's my rod, fixed, attached. So the rod has a length, which is described by the letter L, and it has a mass, which is described by M, and it's basically pinned on one end to the wall by a hinge, and at the other end, I'm going to release this end and release that rest. Okay, so let me just kind of demonstrate what that looks like. Here it is. So if I have my arm is going to serve the purposes of being the wall, if you will. Just need to find one that's small enough. There we are. And this pencil, if you zoom in, this pencil will basically serve as the hinge, right? It basically lets this rod, which is just an ordinary ruler, fall down. And so what I'm going to do is I'm going to set it so that it's on the hinge, and like I've got here. Well, I guess I should turn it this way. So it's the same as what I've got on the board, like that. Yes. And I'm going to release the hinge. So I'm going to hold my finger over the pencil so it doesn't fall. I'm going to hold it perpendicular, and I'm going to let it go. It's going to fall. So I'll do that again. I'll let it go when it falls. So you see the one end's pinned. And ask the following questions. First, well, here's the question. So first question is, there is this point here corresponds to the center of mass. And the center of mass, when it releases, I'm going to argue, it accelerates with some acceleration as the bar falls down. And I want to find out, what is that acceleration at the moment of release, when I'm released at rest. And also, at the moment of release, what are the forces on the bar? What are their magnitudes and what are their directions? So we want to basically figure out what's going on here. So our approach is the same as before. We've got this recipe. So the first thing we do is we say, okay, the bar is released at rest, but that just because it's starting with 0 velocity doesn't mean that the acceleration is also 0. It's beginning to fall. So we don't know what that acceleration is, but we know that it's basically seems to be argued that seems to be the case that basically it's going in some downward direction, which I will define in z, just the same way as we did before. So we're trying to find out that acceleration z. And then the bar is attached to the wall or by this hinge. So we don't know how to contend with that hinge force. It's important to realize that a hinge will do whatever it needs to do to keep this end of the rod in place, which is to say that it will pull on the rod to keep it in place, but it will also push. It will apply a force in any direction so that it ensures that this piece of the rod stays put. So in general, we don't know what a hinge force is. We can't predict in advance either what its magnitude is or which direction it happens to be applying. But we can treat it as basically an unknown force that could apply in any directions. And what we'll do for convenience is we'll break it into components so that we can basically work out what the individual components are. So I'm going to basically define a force which I call the hinge force, H, but I will then break that hinge force into two components, where H sub H is the horizontal component of the force, and H sub V is the vertical component. And this will be the general approach to dealing with the hinge force, is that we will say it's unknown. We will say we don't really know which direction it is, but it will point somewhere, and we will break that force, therefore break that force into two components that are aligned with whatever coordinate system we happen to be using at that time. In this case, because the bar is vertical, we will choose horizontal and vertical coordinates. Okay, but we don't know what that force is. We just know it's applied to the body. So this is now a new force that we're adding to our free body diagram. It's the last new force that we're adding to our force menu. It's the last force on our force menu for the semester, and it applies when we have hinges or the axle to a massive pulley, or things that are essentially analogous to that. So the next step is to do a free body diagram. So we treat the rod as a simple point-like system. I should say, however, there's one piece of information that we do need to give you. Because we're going to be dealing with rotations, we need to know what is the rotational inertia of a long, thin rod that's pivoting about one end. And so I have to tell you that I sub rod, again, this will be given to you for now, I sub rod is equal to, well, it's kind of a weird thing. Turns out to be 1/3 times the mass of the rod times the length of the rod squared. So you notice that all these values for rotational inertia have a factor times the mass times the distance squared. And again, we'll see tomorrow where this comes from. But for now, let's just assume that this is a given for the whole problem. So we've set up the problem. We've defined what we mean by the different coordinate systems. And we're going to proceed with those different forces. So we've got the free body diagram of the rod. So I represent the rod as a point-like object. So what are the forces on the rod? Well, there's the weight, and that's clear. And then there's, how can I say? Then there's the only other force. The only other thing in contact with the rod is the hinge. So that's important. The rod is attached by the hinge. It's not in contact with the wall. So the wall is not pushing or pulling. It's the hinge that's a part of the wall that's pushing or pulling. And as a rule, we don't know whether it's pushed or pulled. And so the question is, which way do these forces go? Well, one force ought to be in the horizontal direction, and another force ought to be in the vertical direction, but which one's which? How do you know? And the short answer is there's no way to know a priori what those forces are. which direction they point. It could point to the left, to the right. You can make an educated guess. So that's the bad news, is you don't know which way they point. And the good news is that if you simply choose a direction, do the calculation, and end up with a magnitude that's negative, that tells you that you got it backwards. Now all you have to do is reverse. So I'm going to make an educated guess. I'm going to say, well, look, the bar has got to hold up at least this end. So my guess is that the bar will apply some kind of vertical force like this. So I'll call that H sub V, and I'll apply, I'll just pick it in a positive direction. It may turn out to be negative, but let's just pick it in a positive direction. And then the next force, well, I don't know if this bar is going to be pushing or pulling at the moment of release. You know, I can't really guess, so I'm just going to pick positive HH, okay? And again, we don't know the value of the hinge force. So either of these components could be positive, negative, or zero, but we set it up in the free body diagram, and we work out what the forces are based on what we know about the motion of the system. So that's nice. So there's one last difficulty. So I've got here, I've got X and Y drawn here, but I will notice something that's kind of interesting and significant, and that is that if I treat the object as an object that is moving, that is a point-like mass, which is to say all of it's centered here, that object, because I'm attached to a hinge, and that hinge has a pivot, so that's obviously my pivot point, that means that every point on this bar moves in a circular path around the pivot. And that means that the center of mass also moves on a circular path. In other words, as the bar comes down, this path is circular. So even though I've set up the problem with X and Y, I could just as well set up the problem with a coordinate system that is appropriate for circular motion, which is to say a coordinate system where I'm going to choose this coordinate in this direction as the centripetal coordinate, because that's towards the center. And then this coordinate here, I will call the velocity coordinate, something like that. So depending on how I want to solve the problem, either coordinate system is fine, but because I've got a circular path, I'm going to basically set it up using this way. Okay. So why do I do that? Because it turns out it makes the calculation of the acceleration central. Oh, by the way, I've got X and Y here, but I've also, somewhere at the beginning of the problem, I defined this as the Z coordinate. So I've got another coordinate, which I'm basically going to call Z downwards, right? So Z and V basically point the same way, which is the opposite of X and Y. So I don't really need this coordinate system. So, you know, having considered it, I'll toss it out, and I'll just, I'm left with C in this direction and Z in this direction. Okay. So again, you can pick any coordinate system you want, but I'm going to use, just for clarity, because I've already defined Z down and C is centripetal, I'll set it up like that. Any questions about that? So again, you don't have to pick my coordinate system, but again, if you line the coordinate system up in the direction of acceleration, which are centripetal and tangential, that's a benefit. It's likely less likely to make mistakes on sign errors. So let's start with Newton's second law in the centripetal coordinate, which is to say the horizontal coordinate. So we say F sub C is equal to M A sub C. So we know that that's equal to M times V squared over, well, what? That's the question. Over R, where R is the radius, but we have to actually think of what that radius is, because in this particular problem, the radius goes from the pivot point, which is at the end of the bar, to the location of the center of mass. That corresponds to R, right? So that radius there is L over 2. So that means that what goes at the bottom here is not, instead of being R, it's L over 2, okay? A technical detail, turns out, doesn't change the answer, but we want to keep that in mind as we go through the problem, that the radius of the center of mass point is half the length distance there. And the happy news is that because I'm releasing at rest, that means V is equal to 0. So that means this term is definitely 0. So the right-hand side is 0. And if I look at the free body diagram, the only coordinate that basically points in the centripetal direction, oh, now I've got H going this way, so I'm going to call that negative HH. That's going to be equal to 0. right? Because I've defined coordinate system there. So in other words, I've now proven that the horizontal component of the hinge force is 0, okay? Just because I've plotted an object that's basically moving on a centripetal path, but it's moving with 0 velocity at the point of impact, point of release. Obviously, if this bar was moving with some given velocity, then this hinge force would actually have to point this way. Again, the negative sign would tell you you've got it the wrong way. You'd have to work out what that is based on the velocity. Okay? So far, so good? I'm going to erase this part here, this equation here, because I need to do the next part. So we've already proven that the hinge force, the horizontal hinge force is 0, so it's only the vertical hinge force that we have to worry about. So let's see if we can solve that. So again, Newton's second law, and now we're in the vertical direction, but we will call that Z for positive down. So we say F sub Z equals M A sub Z, that's what we'd like to find. And we look at the free body diagram then, and we go, the weight minus the vertical hinge force is equal to M A sub Z, which is not 0. So we know that the weight is just equal to mg. That's good. Minus h sub v is equal to M A sub z. Uh-oh. And we get the usual problem. So let me put this in a yellow, highlight the fact that we got a nice equation here, but unfortunately, we have two quantities that are unknown: the vertical hinge force and the vertical acceleration. We know the mass, but we don't know the hinge force. So I've got one equation with two unknowns. I'll call that equation star. Okay. That's as far as we can get. We have not solved the problem. We don't know the force, we don't know the acceleration. So we're stuck now. Now we've got to go to rotations. There's no way out. We knew that, but always try to see how far you can get before you go to rotation. So I'm going to erase this so we can go with that. I'm going to leave this detail of IROD there. Again, this problem I will write up and post online. You can follow it slowly in your own time if you want. Okay, so the next step is we do an extended free body diagram. And the key is, again, we only draw the actual outline of the object and the forces on it. So there's the outline of the object is just the rod itself. And we just put the forces on it that we know have to be there. So it's the same forces as we had here, but we've already shown that's not there, that's 0. So it's really only the two forces, the force on the center of mass of weight and the force on the hinge at the other end, which we call H sub V, the vertical force, which we don't know, but we want to figure that out. The next thing, of course, we need part of the free body diagram is we have to choose a pivot point. So again, obviously, if there's motion around an axle or a hinge, that's where you put the pivot point. And then finally, we have to define a positive direction. So in this case, positive direction would correspond to the motion of the bar and the downward acceleration as we expect. I mean, again, you can always pick counterclockwise or clockwise positive. It's up to you. But if you choose positive in the direction of motion, then that keeps you from getting things tangled when you apply, say, the rolling constraint and so forth in terms of signs. So I will basically choose, in this case, positive in the clockwise direction, which is a little different than I've done before. So that's my extended free body diagram. So then I write down Newton's second law for rotations. And it looks like this. Tau net equals I alpha. So we have I here. So we just have to figure out what the torque is to both of those forces. So we say the torque due to the hinge force in the vertical direction, plus the torque due to the weight. Well, those are the only torques. That's it. That's equal to I, which we said is 1/3 ml squared times alpha. So again, the method is, and again, you want to have this in your pocket while you're doing this. You want to have the definition. So again, this is the definition of torque. off the page? Yeah, it is. Hold on. Deep there. Definition of torque. That tau sub F is defined as R times F times sine phi. You got to have that in your pocket when you get to this point. And you ask yourself, what is R for each of these forces? So the hinge force is applied at the pivot point, so R is 0. So this term is 0. Yay. Plus this weight force, just as we showed before, the weight force corresponds, the R corresponds to this distance here. That's my R, right? So in that case, R is just equal to that length L over 2. And the magnitude of the weight force, we know, that's mg. That's good. And that's positive because I've defined this as a positive direction of torque, clockwise. Remember, the way to figure out the direction of whether the torque is positive or negative is just ask, in the absence of all other forces, which way will that force cause the object to twist? And that is equal to 1/3 ml squared. Okay? So the happy news there is, oh, wait, times alpha. Okay? So the happy news there is I now got an equation that's in terms of all kinds of things I know, except for alpha, but I don't really want alpha. What I want is A. So I need one last piece of work, and that is I need the rolling constraint. Which says that A is equal to alpha R. And we have to figure out what R is again, but that's the same R as we have here. So in this case, A sub Z is equal to alpha times L over 2. Sorry, it's a little crowded. I'm going to rewrite it, all three equations, right? Because that's the distance to the location of the center of mass, which is what the quantity whose acceleration we want to know. So I'm going to erase everything and just rewrite those three equations and make sure we're happy with the algebra. Okay? So and again, I don't usually work out the algebra, but let's just see what we get because it's kind of interesting. Okay, erase that. We don't need that, but let's put these three equations back up on the board. So this is the first equation. And I'll slightly rewrite this, the first equation, by basically bringing this across and bringing that down. So in other words, I'll say H sub V is equal to, basically equal to mg minus m A sub Z, right? So that's basically what we expect there. That makes good sense. So this is the first equation. The next equation, I'll take this equation and slightly rewrite it. I mean, what I'll do is I will, I'll just basically keep the L's here. So we'll say, so this is this one here. I'll say LMG over 2 is equal to 1/3 ML squared. And then finally, I will use this equation here, which says that basically I can rewrite this as alpha equals A sub Z over L over 2. So I'm going to basically substitute that in for alpha. So that will be A sub Z over L over 2. So we just have to watch the algebra when we do this. So let's tackle this second one. What's happening here? I've got this, I've got this, I've got an L squared over L. Oh, by the way, so that means I've got an L here and L squared over L here. So the L's all cancel. So let's cancel the L's. That's nice. I end up with an mg over 2 on this side. So let's just do the numbers here. Mg over 2 on this side is equal to, well, there's a, oh yeah, I can also, notice this, the m's cancel too. So let's cancel the m's while we're at it. So we'll say g over 2, m cancels here, m cancels here. So g over 2 is equal to, well, I get 2/3 A sub Z here. So I get A sub Z is equal to 3 over, oh, look at that. It's equal to 3/4 G. Okay. So in other words, the center of mass is falling, but it's not falling at free fall. It's falling at 3/4 of free fall. It's falling, but not quite as fast in terms of its acceleration as it would be if the object was in free fall. And then once I have this, then I can just plug this in for the h sub v. So in other words, h sub v is equal to mg minus m times 3/4 g. So that's just equal to, well, basically mg over 4. That's h sub v. Okay. Everybody, any questions about how that problem goes? How we go to that problem? Get through that problem? So again, you get to these 3 equations, and the rest is algebra. But the algebra is relatively straightforward, and you typically, again, you do this substitution of the rolling constraint to get rid of this alpha, and then you the m's and l's tend to cancel, and you get the answer you got here. Cool. Questions before I go on?
Yeah, Professor. So we use L over 2 for the radius of the rolling constraint because that's the distance the center of mass is from the pivot.
That's right. So that's really critical. So here, let me just go back to the picture of the situation on the wall, right? So here I'm asking you for the acceleration at this point. Okay. So as the whole bar is accelerating with some angular acceleration alpha. In other words, that depends on the change in this angle. So this is the second derivative of that angle. That's what we mean by alpha, okay? But what I am asking you for is the motion of this point here, which is moving on this path here. And so the radius to that point is L over 2. Now, let me point something else out. Suppose I had asked you, instead of calculating the angular acceleration of the center of mass, instead of asking you the linear acceleration of the center of mass, suppose I'd asked you, suppose I consider a point at the very end of the bar, right? So for example, in this ruler, at the very end of the bar, there's a little tick that corresponds to the 12-inch mark, right? So maybe a little fleck of black paint right here. Well, if I release the bar, that also has some acceleration in the z direction, right? With me? And if I want to calculate the acceleration of this, then instead of using L over 2, I would have to use L.
Okay.
In other words, the acceleration at this end of the bar is twice the acceleration at this end of the bar. Okay. So while the center of mass is moving at 3/4 g, the end of the bar is actually moving at 6/4 g, which is to say 1.5 times g. And of course, this end of the bar is not moving at all, right? So that's the nature of the rolling constraint, is as you move out in distance, the acceleration or the velocity, whatever you're working with, goes up. It's a great question. I just wanted, it was giving a nice opportunity to clarify that. Notice that when we do the free body diagram, even if I'm asking you for the motion associated with one end of the other end of the bar, in order to do the original free body diagram, to treat this object as a point mass, I have to put it at the center of mass. That's what it means to treat an object as a point-like mass. This is the location where the weight gets applied. Okay, good. Any other questions about this problem? How can I put it? If you can do this problem, if you can do that, I'm going to write it down. You should practice it. Make sure you can do it from start to beginning cold. If you can do this problem without looking at your crib sheets and your notes, if you can do it from scratch, so to speak, you've mastered this. This is it. This is the key to, this is some sense of the word, as complicated as rotations are going to get as far as most of the problems I could put on an exam.
Professor, I have a question.
Sure.
So the reason you didn't include the horizontal hinge force on the extended free body diagram is because we calculate it as a 0?
Yes, that's right. But if, of course, I could have included it, and if I had included it, what would the torque to do to it have been? Just for fun. No, I saved myself some work by not including it because I already proved it was 0, and therefore any force at 0 I don't need to put on, once I know it's 0, I don't need to contend with it. But suppose I had not demonstrated that it was 0, or suppose I didn't know that it was 0. I could still put it on my horizontal, my extended free body diagram, but it wouldn't have had any impact because the torque due to the hinge force would still be 0, because the torque due to the hinge force is always 0, because that's where you put the pivot point. Make sense?
Yeah, thank you.
So that's the great thing. So the horrible thing about the hinge force is you have no idea which way it points or what its value is until you actually start the process. That's the horrible thing. The great thing about the hinge force is, by definition, the torque due to the hinge force will always be 0 if you pick that as the pivot point, which makes the torque part easy.
Thank you.
Sure. 2 great questions. Anybody else have any other questions while I'm erasing? Like I said yesterday, the humidity in the room makes the chalk stick more than it did before, because it gets damp and then it doesn't come off. So apologies for the extra craft that doesn't erase easily. So you can see I tend to press large. I'm teaching the summer course on the video with a total distance of about 4 or 5 feet from the camera, but I still use the same chalkboard style as if I'm standing in Strosacker with 250 students. My apologies. All right, so let's do another problem, which we'll take a good look at, and that is the ramp problem, but now with rolling. So you remember the ramp problem. The ramp problem is basically I have a fixed wedge with some given angle theta. That's vertical. And on the wedge, I will put an object, but this time, instead of putting a block on a frictionless surface, I will put a sphere, right? So this is a solid sphere. It will have mass m and radius r. So that's r. So I stick it on there, and this is important. No slip, no slide. Okay? So I actually can demonstrate this, believe it or not, if I get my angle right. I have here, like that. Now, there we are. I have here a ramp, which I'm making out of my hand in this ruler. And I have a little kind of a red, yellow squishy ball. And what I'm going to do is I'm going to put the red squishy ball on the ramp. Let me hold it so you can see it. Okay. And I'm going to release the ball, and it's going to roll down. There it goes. I'll try it one more time just so we see. And the key issue is that it's going to roll without slipping or sliding, which is to say it will, you know, as it goes down the ramp, at every point in contact, it doesn't skid. It doesn't, you know, it doesn't do that. It just rolls. Roll. Kind of rolled off there, but you get the idea. So this is important. No slip, no slide does not mean no friction. No slip, no slide. This implies friction. Okay, because if there was no friction, then this was glare ice, and the ball would just slide right down without rolling. It wouldn't need to roll. It would just be like a brick on glare ice. It would just go down. But if there's, in this case, it's a wooden surface on a rubber ball, there's friction there. But there's no slipping, no sliding. So what kind of friction? It implies static friction. So all of these rolling problems could, in principle, anytime I give you a problem where a wheel rolls or a ball rolls or something like that, and then I tell you no slip, no slide, that implies the possibility of static friction. No slip, no slide. Smooth, I could use the word smooth. Smooth does not imply no friction, just means no bumps. So no slip, no slide means possibility of static friction. And indeed, I'm going to make the argument that there has to be static friction here because that's the only thing, that's the only force that can come into play to cause the ball to roll. Because in order for the ball to roll, there has to be a torque on it. In other words, if I start off, I'm going to release at rest, release at rest, release at rest. If I start off at rest, in order for the ball to roll, it's got to start turning. In order for anything to start turning, there has to be a torque on it. And it's only friction that can generate the torque, as I'll show. Okay? So I want to ask this question. There it goes. What's the acceleration? That's what I'd like to know. Oh, and also, what are the forces? Let's actually work out the forces. Okay? Now, there's a critical piece of information I have to give you in order to solve that problem, and that is I have to give you the rotational inertia of a solid sphere. Okay? And the interesting thing is that the rotational inertia of a solid sphere, so I'll call that ISS, is equal to, well, of all things, it's equal to 2/5 mr squared. Okay? 2/5. Where the heck does 2/5 come from? I won't show you that, at least not in detail, but I will show you that conceptually again tomorrow. For now, just assume that I've given it to you and we have it, okay? Any questions about the setup? So we want to know the acceleration, we want to know the forces. So our strategy will be, as always, to start, well, what do we know? We know the acceleration is there. We know that this thing will accelerate, as it goes down the ramp, it will also accelerate like this, in the clockwise direction. And since this is rolling, the rolling constraint will apply. So we want to keep that in our head. At some point, we're going to need the rolling constraint. So that's in our head. So we now know what that is. So I'm going to pick, I'm going to do the free body diagram, regular free body diagram of the sphere. So it's a marble, if you will, or whatever you're going to call a ball, okay? And for starters, I treat it as a point-like object, and I put all the forces on it. So there's a weight force, like this, and there's a normal force. Now remember, the word normal simply means push. Doesn't mean anything else, it just means a push. And it happens to be a push that's perpendicular to the surface. So in this case, if the surface is pointing up this way, then the normal force will basically point up in that direction like that. So that's the normal force. Okay. And then finally, there has to be, well, I'm implying that there could be friction. And again, your choices for friction are either, again, since it's parallel to the surface, it's either up the ramp or down the ramp. And I will make the argument that, again, if you guess wrong, no big deal, as long as you notice that your answer is negative. A couple of you guessed wrong on the last exam, got a negative answer, and didn't notice that it was negative. So you lost a couple points, not because you got the force of friction wrong, but because you didn't notice that the answer at the end was negative, and therefore you must have got friction wrong. If you notice it, always check your final answer. If you're calculating the magnitude of a force and you get a negative number, you've got the direction of the force wrong. Okay, back to our problem here. So we're going to gas up the ramp, which is the right gas, as I'll show you. And then I need a coordinate system. And in this problem, because I'm accelerating down the ramp, I'm going to pick a tipped coordinate system, where I'll call this coordinate X and this coordinate Y. Okay, so far so good. So let's apply Newton's laws. So we say Newton's second law, F sub Ag. We'll for starters. Well, let's for starters. Let's do the vertical direction first for fun. So Newton's second law in the y coordinate. I'll put this in quotes because we tipped it. Y coordinate. So we say the net force on the sphere in the y direction equals ma in the y direction. Well, we know what a in the y direction is. We know this is a sub x, that's y, that's x, that's y. We know the ball's not jumping off the ramp, so that happily is 0. And then we go n, which is in the y direction, minus, and again, the usual issue of these ramp problems, these angle problems, is I've got some angle. That angle there is the same as that angle there, so that's theta. And the component that's aligned in the y direction is, since that angle is adjacent, that's the cosine. And again, if you guess it wrong, you only have a 50-50 chance of guessing it wrong, but it's not that big a deal. But let's just say it's going to be the cosine. So now this is going to be w times cosine theta. That's going to be equal to 0. And therefore, n is equal to w cosine theta, which is just mg cosine theta. So this is the same answer we get for a brick on a frictionless ramp, or even a friction ramp. It's just the normal force is mg times cos theta. Okay? And now we do the same thing, Newton's second law, in the x-coordinate. So in the x-coordinate, again, let's just write it out. F sub x equals m a sub x. I don't know what a sub x is. But I can look at the forces here. So I say, well, I've got w, if this is cosine, this has to be sine, w sine theta minus the friction, which is pointing backwards, right? And again, I don't label it the kind of friction. I just keep in mind it's static friction. It doesn't really matter. That's equal to max, okay? So in other words, I can just rewrite this as mg minus f equals, mg sine theta. That's important. Don't forget the sign. So we have to rewrite this equation here. Give myself some extra room. Mg sine theta minus f equals ma sub x, which is what I want. And that's a great equation, but unfortunately, it's got two unknowns: the static friction and acceleration. And woe be to you, woe be to you, if you say that the friction is equal to some coefficient times the normal force. That does not apply here. You can't use that because this is not kinetic friction, it's static friction. No slip, no slide. You cannot use this equation. Do not use it here. Simply accept the painful fact that this equation, which is a great equation, is two unknowns, and so your work is not done. Okay? I'm going to carry on. So, well, we knew it. We're not going to put it. The chances of a problem like this having not to deal with torques are pretty small, so now we have to deal with torques. So I'm going to keep this equation in my head. I'm just going to erase everything here. I'm going to remember this. But let's do the extended free body diagram. So I'll leave that equation right there. I can use it. I'm going to keep that part right there. 2/5, because I'm going to have to use that at some point. Okay. So the extended free body diagram. So what do? I draw the object, which is the marble. So I might as well make that reasonably big so I can draw the forces on it without getting too confused. And then I will very lightly, with, I guess I'll use this faint green piece of chalk here, which comes in handy every now and then. I'm going to, kind of put the surface that the marble is rolling on, just so I can keep track of where I am and what's going on. So I've got these forces here, and I need to put them on this marble here. So let's do that one at a time. So the first force I'm going to put on is the weight. Where does the weight go? Where does the weight always go on an extended free body diagram? It goes to the center of mass. And that's always true, and it's never not true. It always goes at the center of mass. So that's the weight. Okay? Actually, I'm going to make this bigger just so you guys can see it really clear. Hold on. Just going to draw it bigger. Like that. That's the ramp. That's my center of mass. That's my weight. Okay? Extended free body diagram. Now, what else have I got? I got the normal and the friction force. The happy news about the normal and the friction force is they're both forces that are applied at the point of contact, right there where the sphere is in contact with the surface. The normal points perpendicular. So that's to say straight from that contact point to the center. So this is the normal force, right? Like that. normal force, pointing this way. And the friction force points parallel to the surface up the ramp. So the friction force points this direction. Okay? So we need to do a couple things to finish. We need to define a pivot point, and we need to find a positive direction. So the choice of pivot point is actually interesting here, and you can solve the problem in two different ways depending on which location you choose the pivot point. But this definition of the moment of inertia, this only applies at the center of mass. In other words, as you'll see tomorrow, this definition only applies at some particular location, which is the center of mass. So that means I'm obliged, since I'm using this, I'm obliged to put the pivot point at the center of mass. Okay, so now I'm going to, again, let me write this equation, or rewrite this equation again, so I've got it handy. mg sine theta minus f equals m ax. So I'm going to rewrite that equation there so I can erase everything here. I can actually do my algebra. And I'll remember the 2/5. Okay, making progress. So we've got that. Oh, we need a coordinate system. Well, the obvious thing is that this thing is rolling down the ramp. That's alpha, so I will define the clockwise direction here as positive. So let's remind ourselves the definition of torque, because I'm always going to want to use it. Torque is equal to RF sine phi. And then I'm going to apply, put this in a box, Newton's second law of rotations, which is tau net equals I alpha. So I've got three forces, so let's actually write down the taus. Tau due to the weight, plus tau due to the normal, plus tau due to the friction is equal to I times alpha. So again, the key issue here is that you have to have, in order to get the net torque, you have to add up all the three torques from each of the three forces and work them out one at a time using this equation and this extended free body diagram. The whole purpose of the extended free body diagram is to do the bookkeeping for each one of these forces. So let's do these forces one at a time. So the first one is quite easy. The torque due to the weight is 0. Why is it 0? Because the pivot point is at the location of the weight. So R, the distance from the pivot point to the force, is 0, so it's 0. That's good. Next, the normal force. What is the torque due to the normal force? Well, we want to draw on the chalkboard the radius R, which goes from the pivot point to, you can just do this lightly on your paper when you're working a problem, to the location where the force is found. That's the vector R. So the happy news is that that vector R is the same as the radius of the sphere, which is given. So this is R. And so that's R. And then the magnitude of the force, we don't know what it is, but it's N. And then it's the sine of the angle. It's the angle between R, which is in pink, and N, which is in white. What is the angle between these two vectors? Anybody? This one points this way, this one points this way.
180.
So the angle is 180. So the sine of 180 is 0. So 0. So this thing basically goes to 0. So you notice that the normal force, because it's pointing straight, any force that's pointing straight at the pivot point always gives 0 torque. That's cool. So the only force left to get that ball rolling is the force of friction. And again, the distance R, that's that same vector, pink R here, which is length R, and F, we don't know what F is. And it points, well, look, that's 90 degrees. So the sine of 90 degrees is just 1. So it's just RF. And that's equal to I alpha. So let's carry on with this. So let's just write this. R times F is equal to I, which we said is 2/5 m R squared. That's it, times alpha. So I've got this other equation, which again has the same two unknowns, F and alpha, same ones as I've got here. Or well, rather not the same ones. That's F, but now I've got alpha. What am I going to do with the alpha? Same thing I always do with the alpha, rolling constraint. You're getting the handle of this now, right? The rolling constraint, which says that A is equal to R times alpha. Well, in this case, alpha is equal to A sub x, which is the acceleration down the ramp, divided by the radius of the ball, R. So I just plug that in. So I get R times F is equal to 2/5 m R squared times A sub x over R. So I've got this equation here and this equation here with two unknowns, two equations and two unknowns. And it's actually pretty easy to do the algebra. The algebra works out like this. I get, well, the R's, that R and those R's all cancel. So I'm left with this equation basically turns into F equals 2/5 MAX. Well, that's interesting. So I just plug that into here, and I will finish up the algebra right. Where can I finish up the algebra with the least damage to the conceptual flow? I guess I'll just try to squeeze it in here. So I get mg sine theta minus 2/5 MAX equals MAX. So I end up with, well, if I bring this from here to here, I'll get 7/5 MAX. The m's cancel. So I end up with A sub x is equal to, when I solve for A sub x, and 7/5 A sub x is equal to g sine theta. So I'll end up with A sub x is equal to 5/7 g. 5/7, oh, it's g sine theta, sorry, sine theta. Which is, if you remember what we got for the block, way back when, the block was just g sine theta, so A sub x now is 5/7 of g sine theta. In other words, a ball rolls down the ramp a little bit slower than a block would go down the ramp if there were no friction. And then once I have this, I can just plug this in here to get the force of friction. Questions about that problem? 5/7, that's kind of a weird number. Going once. Questions? You notice the key idea here. If you don't have friction, you can't get the ball rolling. The force of friction is what torques the ball. It's the only force that contributes to non-zero torque. So without friction, the ball will not roll. No slip, no slide doesn't mean no friction. There's got to be friction here. In order to cause the ball to accelerate faster and faster, there has to be a force of friction. So we've done this recipe 4 times now, where we've set up a problem, we've worked out what we know about the acceleration, we've done the free body diagram, we've applied Newton's laws in a translational form, which is to say F equals ma, to solve the problem as far as we can. Usually we're left, not always, but usually we're left with n equations with n unknowns, which is quite finish. We don't get an answer. We don't have enough equations, rather. So we have to go to the rotational motion. In order to deal with the rotational motion, we write down an X free body diagram. This is so important. There's a 1-to-1 correspondence between the forces on your extended free body diagram and the forces from your regular free body diagram. You have to check, make sure every force on your regular free body diagram appears with the same direction on your extended free body diagram. All you're doing is picking them up and moving them and putting them here. Once you have the extended free body diagram, you write down Newton's second law, but for rotations, and then you work out what the torques are using the diagrams, force by force, with this definition, right? So remember, this equation is Newton's second law. This equation is the definition. You need the extended free body diagram in order to work out what the values are of R and sine phi. Many times, as in this example, phi will be either 180 degrees or 0 degrees or 90 degrees, in which case the sine is easy to calculate. All right, I've got one more thing to say, and then I'm only going to take 3 minutes, and then I'll let you go. I'm just going to set up what we're going to do tomorrow. And for tomorrow, I will have one short video clip and one asynchronous content lecture, which will be on the exciting problem of how you calculate inertia, rotational inertia, which I actually will show you, and you'll need to understand conceptually, but I'm not actually going to insist that you know how to do it for any exam. I'm just going to show you how it gets done, but technically, it's literally just calculus. So I don't want to have everybody being required to demonstrate that they can do calculus in a physics problem just for the purposes of showing me that you can do the calculus. But let me just set things up. I want to go back to the ramp problem. There's the ramp. We got the ball. Again, the same thing. I is equal to 2/5 r squared, which those are given. Angle theta is given. And now I'm going to give you one more thing. I'm going to have the ball basically roll down the ramp so that it rolls from here. I'll make this kind of smooth to here. Again, rolling, no slip, no slide. Rolling. Woo-hoo! Off it goes. It's rolling. What's the velocity of the ball when it gets to the ramp? When it gets, again, release and rest. Okay? So how do we tackle this problem? So there's a hard way to do it, which is, we'll give you the right answer, and that is that you can work out what A is, and therefore you can work out, and what alpha is, and therefore you can work out the trigonometry of this distance and figure out by constant acceleration all of these details. But that's the hard way to do it. And again, that would be using the toolbox of Newton's laws, which we've now extended from translational to rotational motion. So by analogy now, we want to use a different law, different toolbox. And if this were simply a block on a frictionless ramp, the easy way to do it is to say, oh, I've got an object here and I've got an object here. It's like the child on a slide with no friction. I could say, oh, that's great. No friction means I can use conservation of mechanical energy. So in other words, conservation of mechanical energy would say that the total energy is equal to the total energy prime, which is to say U plus K is equal to U prime plus K prime. That's great. And that would be wonderful, except for this annoying fact that what about the conditions? So we have the weight, the normal, and the friction. So the weight is conservative. Yay, it means we can use this, at least so far. The normal force is not conservative, boo, but it does no work because the normal force is always perpendicular to the direction of the motion, the path. So the normal force is not conservative, but it does zero work. Yay, so far so good. What about the friction force? The friction force is not conservative. Furthermore, the direction of the friction force, annoyingly, is lined up with the direction of motion on the path. So you cannot trivially assert that the friction does zero work. So we got a problem. In principle, you cannot use conservation of mechanical energy to solve this problem. Especially, you can't use it if you treat this object as a point-like object. But if we extend our notion of kinetic energy just a little bit, we can use it. And the rationale basically goes like this. At the point of contact, there is a force being applied, but at that point of contact, there's no slipping and no sliding. Therefore, there's no work being done against that point of contact. You are accelerating the ball, however, and that means that you've got to expand your notion of kinetic energy. So that's what we're going to do next time. We're going to take the notion of kinetic energy, kinetic energy, which is equal to 1/2 mv squared, and we're going to extend it so that there's another component associated with rotational motion. And we're just going to see if we can get away with the rotational analog, which is to say, well, 1/2, the rotational analog of m is just I, and the rotational analog of v is just omega squared. Oh, it turns out this works perfectly. And that lets us solve this problem for conservation of energy, which I will show you how to do tomorrow. So that's all I've got for today. Anybody have any questions about either anything I've done today, the previous problems, or anything that you want to ask me about? Otherwise, we're done for the day. So I've set this up, but I haven't solved it yet. We'll do that tomorrow. Going once. I will have office hours today. I forgot to mention that at the beginning of class. They'll be at 4:30. I think I've already posted the Zoom invitation. So don't hesitate to track me down if you have questions about anything then. If that time doesn't work, just send me an email, and I will be glad to answer your questions. I will post yesterday's and today's practice problems on the web page as soon as I can this afternoon. Otherwise, that's it. Everybody have a good day. Stick with the effort. We're almost done. Got basically a few days this week, a few days next week, and we're done. Talk to you soon.